And as I said, this first week we're just going to cover basic math operations with different types of numbers. But I want to start out with something even more basic because I've found through the years that a lot of people's struggles with the more complex math topics come from the fact that they don't really understand the most basic of math topics. For example, we're going to start out with probably our most basic topic, also the most misunderstood topic, and that is, what is a number? If I put a 4 up here, give me a show of hands. How many of you would tell me that that's a number? Most of you would, right? Some of you got your hands down because you know something's coming. Right? 4 is just an amount. It's what we would call a numeral. To be a number, technically it has to have two parts. It has to have that amount, and then it has to tell us what it is. For example, 4 cows. Now it's truly a number. It tells us how many, in this case the 4, which I'm going to refer to as the count, and then of what, or what the label is. In this case, the cows, which I'm going to call the name. Now, some of you might be thinking, oh no, here's another one of those uptight math teachers who's going to make us label everything. That's not my purpose here. I'm not going to mark it wrong if you don't put, 3 pails or whatever on your answer. If you just put 3, that's fine. But for now, I want you to see those two parts because it's very important when we look at our different types of numbers. Those two parts define how those operations are done and why they're done that way. So let's look at those two parts of a number in our most basic math operations. Addition and multiplication. Some of you might be thinking, where did subtraction go? Subtraction and addition are really the same operation, just done forward and reverse. So anything that applies to addition also applies to subtraction. And the same with multiplication and division. This might be a good spot to say, by the way. I realize that, especially this time of night when I'm tired, my handwriting can be horrible. I also suck at spelling too, so that's an added bonus. But if anything ever appears up on the board that you don't recognize, I assure you it was intended to be English. I probably either just horribly misspelled it or my handwriting is that bad. So I will not be offended if you stop me and ask me what something says. So let's try to add a couple numbers here. Let's look at 4 inches plus 7 inches. What do we get? Not everybody at once. 11 inches. There we go. Not really groundbreaking information there, but there's a couple of things if we look at our two parts of a numbers that I should point out. If we look at our counts, the 4 and the 7 become 11. We combine the counts. If we look at our names, inches and inches became inches. We keep the same name. So again, probably not horribly life-changing information yet. Probably not quite worth your $400 for the course. But if we look at multiplication and how it's different, 4 inches times 7 inches is going to become what? Again, wait your turn. There'll be plenty of time for everyone. 28. Not inches, but inches squared. For multiplying two measurements like that, chances are we're looking at an area. We're multiplying 7 inches times 4 inches. I realize it's late at night. I'm starting to see vapor trails too, so I'm just picking on you if you're not talking. But I won't take it personally. So let's look at our counts. Our 4 and our 7 become 28. We still combine the counts. This time we're multiplying, so we combine them with multiplication. The difference comes in the names. Inches and inches this time become inches squared. When we multiply, we also combine the names. Now at this point, you might not think that that is a big deal, but it really is. All of the processes we use for operations with all the other forms of numbers come from that subtle little point right there. In fact, that even determines what we can use in each operation. For example, it's late, so I'm going to play with it a little bit. So I have 4 cows plus 5 boys. Do I get, does that work? 9 cowboys? No. What if we reverse it? 5 boys plus 4 cows, do we get 9 boy cows? Okay. Anybody with a farming background here? Nobody? If you did, you could tell me that is a whole bunch of boring. Okay, long way to go for a joke. I'm a math teacher. It's late at night. I'm required to have a really stupid sense of humor. You'll get used to it. But there's a point behind that. The reason we cannot combine cows with boys is because when we add numbers, we're going to keep the same name. That implies that we start with the same name. On a little bit more serious example, if we had 5 feet plus 2 pounds, what do we end up with? Well, 5 feet and 2 pounds. They have different names. We cannot combine them with addition or with subtraction. But on the multiplication side of things, if I had 5 feet times 2 pounds, when we multiply, we're going to combine counts. So 5 times 2 makes 10. There we go. And feet times pounds is just going to become foot pounds. If you're into engines, that's a unit of torque. Or if you're in structural design, that's a unit of moment. When we multiply, since we're going to combine the names, we do not have to start with the same name. Now, at this point, that maybe is starting to be interesting, but not seeing the huge importance to it. But it shows up when we look at our other forms of numbers. Let's start out with everybody's favorite type of number, fractions. Okay, I realize that if I ask people, yeah, thanks. I realize if I ask people on their way in the door, 4 out of 5 people would say that the part they hate most about math is fractions. The other one would probably say the teacher. Let's review. What's the top number called? Numerator. Very good. Bottom number? Denominator. But what do those words mean? Well, to numerate means simply to count. To denominate, just like different denominations of organizations or bill of money, to denominate means to classify or to give a name. So a fraction, the numerator and denominator, are really nothing more than a count and a name. Just like having 3 inches or 3 cows, here we have 3/7. The 7 is not a number, it is a label. So if we go to add fractions, 3/7 plus 2/7, if we go back to 3rd grade or so, think about the first time we were taught to add fractions. That 3rd grade teacher told us to add or subtract fractions, you must have common denominator. Again, that's not a special rule for fractions. Anytime we add numbers, we must have the same name. They also taught us when we add the fractions, what are we going to do? What a really talkative group. We're going to add the numerators. 3 plus 2 is 5. And keep the common denominator, 7. Again, that's not a special rule for fractions. Anytime we add numbers, we combine the counts and we keep the same name. It just looks different because fractions look a little different. So if we see something like 1/3 plus 2/5, can we add those the way they're written? No. In our second hour of class, we're going to look at how do we change those so that we can add them. But for right now, they have different names. We cannot combine them with addition or subtraction. On the multiplication side, though, looking back at that 3rd grade teacher, how did they tell us to multiply fractions? Straight across. 3 times 2 is 6. 7 times 7, 49. Again, that is not a special set of rules for fractions. Anytime we multiply numbers, we combine the counts and then also combine the names. If we have the 1/3 times the 2/5, do we have to have the same common denominator to multiply? No. Anytime we multiply, we do not need the same name. We're just going to combine the counts. 1 times 2 is 2. 3 times 5 is 15. So again, the rules for fractions are really not anything unique. They're the exact same rules we use for whole numbers. Decimals. 0.21. Now the formal way, the actual way you would pronounce that would be what? 21 over 100 or 21 hundredths. And when we write it out that way, it's obvious to see what's the count and what's the name. So if I'm adding decimals, .21 plus 0.3, is that going to work? Why not? The difference is, the decimals don't line up. We were always told you have to line up the decimal points. Why? Well, the third grade teacher said so, right? Well, if we look at this, this is 21 hundredths. This is 3 tenths. Right now they have different names. Fortunately, we can just do that, putting a 0 there, and now that becomes 30 hundredths. And once we've done that, the decimal points will automatically line up. We can add them. 21 plus 30 is 51. Where's our decimal point go? You just bring it straight down. Because when we add numbers, we keep the same name. So 21 hundredths and 30 hundredths have to become 51 hundredths. Bringing that decimal point straight down is just keeping the same name. When I multiply, do I have to line up my decimal point? No, we don't. Because when we multiply, we do not need the same name. 21 times 3 is 63. Where does my decimal point go? Add a 0, put it there. Can anybody tell me why? Perfect. We were taught to count 1, 2, 3 decimal places in the problem, 1, 2, 3 decimal places in our answer. But again, why? Because that's what we were told, right? This is 21 hundredths, and this is 3 tenths. And when we multiply, we do combine the counts. 21 times 3 is 63, but we also combine the names. Hundredths times tenths is thousandths. So when we're counting up those decimal places in the problem and making sure we put that many decimal places in the answer, what we're doing is combining the names. We can go a step further. Algebraic numbers. 4x. Now, some people cringe when we hit this point because they don't like having the letters or the variables mixed with our numbers, but it really behaves exactly the same way as any other type of number. The 4 here is a count, and that looks like a C, and the x is the name. And if I wanted to add an algebraic number, let's do 4x plus 11x. What am I going to get? 15x, right? Yeah, adding. A lot of people are, well, is that x or is it x squared? Well, it's just like any other addition. We combine the counts. 4 plus 11 is 15, and we keep the same name. So x plus x stays x. If we were multiplying, what are we going to get? 44x squared. Good. We combine the counts. 4 times 11 is 44. And just like inches times inches became inches squared, x times x becomes x squared. What if I have 5x plus 2y? What do I get? Perfect. 5x plus 2y. Just like up here where 5 feet plus 2 pounds has to stay just 5 feet plus 2 pounds because they have different names. 5x plus 2y cannot be combined with addition or with subtraction because they have different names. However, 5x times 2y would be 10xy. Perfect. We combine the counts. 5 times 2 is 10. And just like feet times pounds became foot pounds, x times y becomes xy. Now I realize we just flew through like 4 math topics all at once. We are going to go back and look at some of them in a little bit more detail. But I wanted to show you guys the big picture so you can see how all of it fits together. Now we're going to step back and we're going to look at how does this really apply to the stuff that we do every day, our basic calculations. I'm going to apologize for the next 10 minutes because it might be even a little bit more basic than what we just covered, but I'm going to look at operations with whole numbers quick. To see how this applies to our operations with whole numbers, the concept that ties it all together is the concept of place value. It's another one of those really simple concepts that is way more important than what people give it credit for. Now, I realize you guys all know your place values, so let's just throw them out here. Starting at the end of the number or the decimal point and working backwards, this last one is the ones, then tens. So you guys got to help me out a little bit here. Then hundreds. And those are actually our 3 place values. That is our base group. Next we have the thousands group, and the same 3 place values repeat over and over again. Ones, tens, and hundreds. And then we have the millions group and so on. And if we're going to name a place value, we name its place and its group. So this is the 10 thousands, and this is just the tens. We're not going to go over that in great detail, but just having it out there is necessary to look at our operations. The way that applies is if we have something like 264. What we're used to seeing as that number is really just an abbreviation of the real number. The full number is really like this: 2 hundreds and 6 tens and 4 ones. Some of you may have seen that referred to as expanded form of a number. The reason that is important is it now shows us that every digit of that number is a count and a name. So when we go to add these multi-digit numbers, let's have like 325. I'll write that out. So 300s and 2 tens and 5 ones. When we add numbers, we can only combine things that have the same name. We were always taught that when we add numbers, you have to line up the columns. Well, the reason being is these 6 tens can only combine with other tens. The 200s can only combine with other hundreds. So lining up the columns is a way of making sure we only combine things with the same name. So once the columns are lined up, we can just go ahead and add 200s and 300s is 500s. 6 tens and 2 tens is 8 tens. 4 ones and 5 ones is 9 ones. So 589. But some of you may have caught that I did something a little odd there. Can anybody tell me what it is? I did things backwards. I started on the left and worked to the right. Normally, we start on the right and work back to the left. Can anybody tell me why? In case we have to carry. Very good. Let's do 275 plus 396. Normally we run it when we do addition. We start on the right and work our way back to the left because we run into problems like this. 5 plus 6 is 11. Well, we can't have 2 digits there, so what do? We keep this one and we carry that one. 1 and 7 is 8, plus 9 is 17. So we keep the 7, carry the 1. 1 and 2 is 3, plus 3 is 6. Now again, I don't mean to show you a lot of examples of simple addition, but I do want to show you that this isn't the only way to add. We've always been taught that in math there's one way to do things. This process of carrying is actually only a couple hundred years old. Before it was done that way, addition looked like this. 2 plus 3 is 5, 7 plus 9 is 16, so 6 drop the 1. 5 plus 6 is 11, so 1 drop the 1. 671. Now, I'm not trying to change the way you add numbers, but I'm just trying to make the point that there's not just one single right way of doing things. I could actually show you 4 or 5 other ways to add numbers. I'm not going to because I don't want to confuse you, but they're out there. On the realistic side of things, I know that you have calculators and you're going to use them. When you get to 3-digit numbers, you're probably not going to start writing things out by hand. So before you start punching things in the calculator, I want you to think a little bit about what you expect your answer to be. For me, I would look at this and say that's about 300. This is about 400, so I'm expecting my answer to come out to be close to 700. The reason I say that is, especially if you have fat fingers like I do, the calculator has a huge chance of mistakes. I could punch in something like this and do this. 421 is not the right answer. What went wrong? The 7 didn't register when I pushed it. If I'm not paying attention, it's really easy to write down 421 because that's what the calculator says and go on my way, and everything I do after that is wrong because of that wrong answer. Just as easy to hit 2 keys at once and not notice it. So try to have that idea in your head of what you expect the answer to be before you punch it in the calculator. Subtraction, we're not going to get into because it works the same way. Same concept of adding, lining up the columns because you can only combine things with the same place value. Let's talk just briefly about multiplication. This one I'm going to write out in long form as well, so that is 2 hundreds plus 3 tens plus 1 1. This is 3 tens and 2 ones. When we multiply, do we need the same name? No. So the 3 tens here not only can be combined with the other 3 tens, but it can also combine with the 2 ones. In fact, every digit in this number can be combined with every digit in this number. So that's really all long multiplication is an organized way of making sure that every digit in each number combines with every digit in the other number. So we normally start with the last digit of the bottom number, the 2 ones, and we go from there. So we combine that with the 1 1. Just like before, you combine the counts and you combine the names. 2 times 1 is 2. 1s times 1s is still 1s. Then move on to the 3 tens. 2 times 3 is 6. 1s times 10s is just 10s. Going on to the 200s. 2 times 2, 4. 1s times hundreds is hundreds. Now we're done with the 2 ones. We're going to move on to the 3 tens. What have we been taught to do down here before we move over? Put in a 0 down here. And the reason for that 0 is going to become apparent in just a second. So 3 tens times 1 1. 3 times 1 is 3. Tens times 1s is tens. We had to put that 0 in here so that we keep our tens lined up with our other tens. Now 3 tens times 3 tens. 3 times 3 is 9. Tens times tens is hundreds. And 3 tens times 2 hundreds. 3 times 2, 6. Tens times hundreds, thousands. Very good. And then, of course, you just add the columns. Combine the things with the like place values. That's 2 1s. 6 and 3 is 9 tens. 4 and 9 is 13, so 300s carry the 1. 7,000. So 7,392. Now, once again, I realize that you're not going to do a lot of long multiplication by hand. But I do ask if you're going to use the calculator. Once again, you look at this and say, that's about 200. That's about 30. 2 times 3 is 6. Hundreds times tens is thousands. I'm expecting my calculator to spit out an answer around 6,000. 7,392 is a little bit bigger than that, but it's in the right ballpark. So we know it's at least a reasonable answer. Now, before we take our break, I want to show you long division, mainly because division is the one operation that has been altered and shortened the most to the point where you don't even recognize what it really is anymore. To talk about division, let's look at the definition of multiplication quick. Step back just a little bit. Right around first grade, when we first learned how to multiply, before we memorized that 5 times 3 was 15, how did we figure that out? Oh, there you go. Yeah, repeated addition. 3 5s. 5 plus 5 plus 5 gives us 15. Multiplication is defined to be repeated addition. Now, I said earlier that division was the reverse of multiplication. So it makes sense that division is repeated subtraction. 24 divided by 8 is asking us, how many times can I subtract 8 from 24? 24 minus 8 is 16, that's once. 16 minus 8 is 8, that's twice. 8 minus 8 is 0, that's 3 times. 24 minus 8 is 3 because we can subtract 8 from 24 3 times. There was nothing left over, so it's just 3. If there's something left over, that's where our remainder comes from. So we have 14 divided by 3. 14 minus 3 is 11, that's once. Minus 3 again is 8, that's twice. Minus 3 again is 5, that's 3 times. Minus 3 again is 2, that's 4 times. We can't subtract 3 anymore. So that's telling us that 4 divided by 3 is, or 14 divided by 3, sorry, is 4 with a remainder of 2. Now we'll look at other things we can do with that remainder in a little bit, but for now, that's where the remainders come from. So anyway, on to long division. What does this have to do with that big long division that we've always been taught? Well, as I said, long division is the one operation that looks the least like what it really is. Let's take 68,492 and divide by 21. When we just said that division is repeated subtraction. Now, I'm not about to start subtracting 21 from 68,000. I don't have that kind of time. But if I could subtract the 21 in big bunches, it would go a lot faster. And that's what long division really is just a way of subtracting that number in big bunches, several times at once. The way we do that is we look at the place value of the number we're dividing. This first place value is what? 10,000, right? So we get 10,000 times 21, that is 210,000. Can I subtract that from 68,000? No. The next place value is the thousands. 1,000 times 21 is 21,000. Can I subtract that from 68,000? Yes, I can. In fact, I can subtract it if more than once. How many times can I subtract it? 3 times. Very good. It'll be 63,000. Which would give me 5,492. Now what I really just did there is I subtracted 21 1,000 times 3, or 3,000 times. Now I move on to the next place value, the 100s. 100 times 21 is 2,100. Can I subtract that from the 5,492? Yes. How many times? Twice, right? 4,200. So that is 1,292. Now what I just did there, I subtracted 21 100 times 2, or 200 more times. If I keep going, next place value is 10. 10 times 21 is 210. Can I subtract that? Sure I can. How many times? 6 times, right? It's 1,260. Just 32 left over. So that would be 10 times 6, or subtracting 21 60 more times. Finally, I'm just down to ones, or 21 itself. I can subtract that once with 11 left over. So what that's telling me is 68,492 divided by 21 is 3,261 with a remainder of 11. Now you might be looking at that thinking that looks absolutely nothing like the long division I was taught. And you're right, on the surface it doesn't. But it's really exactly the same process. And let me show you how, just really quickly. The way we were taught to do this is you start with the 21 and you look at the first digit. Does 21 go into 6? No. So you leave it blank above the 6. That's what we did here when we started with the 10,000 and we realized we could not subtract 210,000. Move to the next place value, the 8. Does 21 go into 68? You bet. 3 times. Since the 8 was the last digit we used, the 3 goes above the 8. That was the thousands. 3 times 21 is 63, leaving us with 5. Now at this point it looks different, but let me show you how it's exactly the same. If we look at this here, this line, those 2 lines, and these 2 lines are exactly the same, only we've left off the zeros. And then of course we would bring down the next digit, the 4. 21 goes into 54 twice. That is 42, and we subtract. Now once again, it looks different, but you see that this line and this line are exactly the same as we have over here. We've just left off the zeros. Now I'm not going to bother finishing that out because I'm assuming you guys can handle it. And again, realistically, long division is the one operation I refuse to do by hand if I can avoid it. That almost always goes in the calculator for me. So I realize you're going to be punching that in most likely. So once again, do an estimate. 68,000 is roughly 70,000. 21 is roughly 20. You go to divide that, it doesn't work out really perfect. 7 divided by 2 is like 3.5. So you can either go with 3 or 4, it doesn't matter. Then the zeros, instead of combining them like you would with multiplication, you would cancel them out. 1 0 here cancels 1 there, you're left with 3. So your estimate is that that's going to be close to 3,000. We had 3,261, so when the calculator spits that out, we know we're in the right ballpark. Any questions? Okay, let's take a break. It is 6:22. Let's come back at 6:32 and start up from there.